So this video is going to be a little discussion on logarithmic differentiation. When you have to use it, when you can use it, and then obviously how you use it. So we'll talk about the process, we'll show how to use it for both of these examples. The process is going to involve these properties of logarithms that you would remember from your Algebra 2 or pre-calculus course. So if you have the logarithm of a product, you can break that up into the sum of two separate logarithms. If you have the logarithm of a quotient, you can break that up into the difference of two separate logarithms. And if you have an exponent applied to something that's within a logarithm, you can actually bring the exponent down in front as the coefficient of that logarithm. So why in this particular function, if we're looking for the derivative of it, why is logarithmic differentiation pretty much required in order to build a derivative? So I've got two rules that you would be familiar with if you're in your Calculus 1 course. Power rule says we're going to find a derivative by multiplying by the exponent and subtracting 1 from it. This is probably what you use more so than anything else in your calculus course. Here's the catch. Power rule only works when the power is a real number. Check out the power here. Power is a variable. Power rule is off the table because we don't have a real number in the exponent. We've got this other formula that you've probably seen a little bit later in your derivatives unit than you saw the power rule, but it says for any constant a that's greater than 0, I can find the derivative of a to a power by copying the same exponential function and then multiplying by the natural log of the base. This works if the base is a constant that's positive. Check out the base of this function here. It's got a variable in it. If you've got a variable in both the base and the exponent of a single term, and you would like the derivative of that function, you are going to need to use logarithmic differentiation. So that's why logarithmic differentiation is required here. It essentially gets us past the issue of having an x in the base and in that same exponent. So how do we use the process? So what we're going to do when we utilize the strategy of finding a derivative with logarithmic differentiation, first step is going to be to take the natural log of both sides of your equation. This is an equation, so I can take the natural log of both sides. And the reason why that's a useful step is because if you think about the right-hand side, one of those properties said, hey, we can bring what's in this exponent down in front as the coefficient of that logarithm. Now, if you look at the two sides of this equation, this line of the equation right here, I now no longer have a situation where there's an x in the base and an x in that same base's exponent. I can take the derivative on the right side of the equation, so that's exactly what I'm going to do. Now, the notation I'm using here is going to be used in our second example of the day as well. Second example gets a little lengthier, so you won't necessarily see this played out as much or written out as much. I'm taking the derivative of both sides with respect to x. I'm going to talk initially about the right-hand side. This should be the side that you understand a little bit more. This is x times natural log of sine of x. This is going to require a product rule. So here's the derivative of x. Here's the original second piece. And then I'm adding on the original first piece. And then I'm multiplying by the derivative of natural log of sine of x. I do have to use a chain rule for that. So I'm going to have 1 over the same inner function, sine of x, and then times the derivative of that inside function. Derivative of sine of x is cosine of x. If you want to clean this up a little bit, there's another step or two that we're going to do, so it's definitely nice to do that. I don't have to show this times 1. And then if I'm multiplying x with what basically is cosine of x over sine of x, that's really cotangent of x. So the right-hand side simplifies to what you see in this set of parentheses. Now, the left-hand side we haven't discussed yet. The left-hand side is a little different. If you've already discussed a process called implicit differentiation, you should be pretty comfortable with this. If you haven't, here's what we're doing. We know that y is a function of x. So when I'm taking the derivative of natural log of y, I know y is a function of x. What I essentially have is an outside function, natural log, and an inside function, y. So I'm going to have to use a chain rule on that left-hand side for the derivative of it. And just like we did over here for the derivative of natural log of sine of x, I'm going to do 1 over the same inner function, and then I'm going to multiply by the derivative of the inner function. Now the derivative of y with respect to x is dy dx, or y prime, whichever notation you're choosing to use. Now what makes this require an extra step or two to build a derivative Normally, when you take the derivative of both sides of the equation, you get directly to y prime or dy dx or f prime of x, whatever notation it is that you're using. That's not the case when we use logarithmic differentiation. So this step will be pretty consistent at the end of this process. I need to isolate my derivative. Rather than having this 1 over y multiplying dy dx, I'm going to multiply both sides of my equation by y to make sure that dy dx is isolated. And on this line here, this is not necessarily incorrect, but you would typically prefer if your derivative depends only on a single variable. So rather than having this line, second to last line is my answer line, I know that y is equal to sine of x to the x power, so I'm simply going to replace that y with sine of x to the x. So it's definitely a little bit different of a process. There's not really a formula that you would memorize to utilize this. It's something that you're just kind of using your collection of already known derivative rules and formulas in order to do. Again, it's required in this situation because there's an x in the base and there's an x in the exponent. That other function that you saw in the opening screen, we want the derivative of this function. Now, you know when you take a derivative, you would prefer to see powers rather than roots. So if I have all of these things, all of these quantities in the parentheses under a fifth root, I can rearrange that to be able to take the derivative a little bit more effectively by recognizing that a fifth root is really a 1/5 power. And if I have something to the fourth to the 1/5 power, multiplying those powers gives me 4/5 as the power on x minus 3. I'm going to get 1/5 as the power on the x squared plus 1. And then the power here is 3, so something to the third to the 1/5 is going to give me a resulting power of 3/5. This is now in a little bit more beneficial form for us to try to take the derivative of. So what is option 1? Option 1 does not require logarithmic differentiation. That's why we've said optional to use the process for this particular derivative. So what would you have to notice to take this derivative? Well, the overall build of this function is that it's a quotient. So what you see I've structured here is a big quotient rule. You see my division. Here's the original numerator, or excuse me, the original denominator. This is going to be for the derivative of the numerator. Here's the subtraction, and then the original numerator, derivative of the denominator goes here. There's the original denominator squared. Now, why is this pretty messy? Think about this numerator. This numerator is a product. So when you take the derivative of the numerator in this position, you're going to have to apply a product rule. So you see the product rule structure built within this blue set of parentheses written out in red. And then what are you going to do when you take the derivative of this piece of the product? Well, you're going to have to use a chain rule in this position. When you take the derivative of this piece of the product, you're going to have to use a chain rule in this position. What about when you do the derivative of that denominator? You're going to have to do a chain rule here. So if you don't mind building a quotient rule derivative that utilizes a product rule and 3 chain rules, you can take the derivative without logarithmic differentiation. If you would like an alternative to having to do what we're suggesting here, how does logarithmic differentiation provide that? So same manipulation of the original function, right? We've rearranged the root as a power and raised everything, all the quantities within that root to the 1/5 power. If I'm using logarithmic differentiation, my first step is going to be to take the natural log of both sides of my equation. On this side of the equation, there are multiple properties of logarithms that can be applied. First of which is going to be I have a quotient within this logarithm. I can break that up into 2 separate logarithms that are subtracted. Now, with this initial logarithm, you'll notice that it's a product. So one of those other properties of logarithms allows us to break the product within a single logarithm up into 2 separate logarithms that are added together. Now, within this logarithm after the subtraction, you see there's an exponent within that. I can bring that exponent down in front as the coefficient of the logarithm. And I can use that property to manipulate this logarithm and this logarithm as well. So that's what you're going to see happen as we go from this line to the line beneath it. This exponent came down in front as the coefficient of that logarithm. This exponent came down in front as the coefficient of that logarithm. If you look at this line right here, do I still have a chain here and a chain here and a chain here? Yes, but I've gotten rid of the quotient, I've gotten rid of the product, and I'm going to not have as tough of a time taking my derivative on that right-hand side by doing this. So it's kind of up to you. What would you prefer to do? Would you prefer to structure a bunch of derivative rules nestled one within the other and all having to fit together successfully? That's kind of messy, but it's not incorrect to take the derivative that way. Or are you comfortable with applying these properties of logarithms and recognizing that we can bypass a lot of those rules nested one inside the other by using those properties of logarithms, taking the derivative of both sides of this equation? Again, on the left-hand side, I know y is a function of x. Here's what the function of x, y is. So I'm going to use a special chain rule. 1 over the inside function times the derivative of the inside function. And like we mentioned in the prior example, that will be pretty consistent when you're using the process of logarithmic differentiation. On the right-hand side, I can copy this constant into my derivative, and then I'm going to have 1 over the inside function times the derivative of the inside function. I'm adding on, constant copied in, 1 over that inside function times the derivative of it, subtracting off, the constant copied in, 1 over this inside function times the derivative of it. I do want to solve this for dy dx, so I'm going to multiply the y across to isolate dy dx, so you see that that's been done right here. And then if I multiply these three components together, top times top times top, bottom times bottom times bottom, I'd end up with this for my initial fraction. Top times top times top gives me 2x in the numerator. Distributing 5 into this denominator gives me 5x squared plus 5 there. Again, top times top times top, 6 in the numerator. Distribute 5 into this denominator, and you have your derivative. So it is a matter of opinion. What's easier? Do you like using these properties? There's very little calculus on the screen. The only line of calculus was this line right here. Everything else was algebraic manipulation. Or are you comfortable doing a great big huge line of calculus, carefully nestling one inside the other and making sure everything's fit together the appropriate way? Both get you a successful derivative. Either way you do it, this derivative is obviously pretty messy. Pay attention to the directions of the problem. Do they say just take a derivative? If that's the case, either option's okay. Do they say use logarithmic differentiation? Well, then you're going to have to go this route.